Analytical chemistry. We're going to look at using certain pieces of equipment and technology to aid in the identification of compounds. All right, let's define the term first. Analytical chemistry is the study of the separation, the identification, and quantification of chemical components of materials. So, these various instruments and techniques we're going to look at are going to separate a sample. We're going to identify certain things about that sample. Quantification is determining how much of these different components are in a particular sample, and we'll find that several of them are used to actually identify any particular structure or compound. And just to go over some of the reasons why analytical chemistry is important, and these are just some examples. Okay, so sometimes you're going to want to determine what the concentration is of a certain substance. Things like analyzing a water supply for a community to tell how much lead or arsenic or other contaminants might be in a water supply. And if you ever look on the side of your food, okay, there are nutritional content information on those. Those are done using analytical chemistry. In drug development, sometimes you need to determine the structure of a new drug, and you would use analytical. In drug manufacturing, you want to make sure that the Tylenol that you make has the correct amount of acetaminophen in it, all right, or the purity of a substance. A lot of that is just in manufacturing because your customers want to make sure that you are supplying the material that you say you are. If it's 95% pure, they're going to test it to make sure it's 95. And then in medical testing and also crime scene investigation, read that as forensics, to determine the chemical composition of a substance or the identity of an unknown substance. There are several different analytical methods that we're going to take a look at, the first of which is infrared spectroscopy, mass spectroscopy, which we looked at in general terms last year. Then we have nuclear magnetic resonance spectroscopy, atomic absorption, AA spectroscopy, visible and ultraviolet UV-vis spectroscopy, X-ray crystallography, and chromatography. For most of these, if not all of them, we're going to be looking at how to analyze the results from these techniques. So not necessarily how the instrumentation itself works, but how do we use the information that they give us. And again, a key point here are a lot of these techniques are used in combination to determine the structure or the identity of a compound. All right, so let's consider these following molecular compounds: C3H8, C3H6, C3H4. Take a moment and draw reasonable structures for each of these compounds. Okay, so if you drew those structures, this should be what you drew for the C3H8. This would be the C3H6. And these two structures, either one of these would be appropriate for a C3H4. Hopefully what you notice is that these molecules change in their degree of saturation, if you remember this term. Okay, if you don't, let's take a moment and define that term. Okay, so a saturated hydrocarbon is a hydrocarbon that contains the maximum number of hydrogens, meaning that that hydrocarbon is going to contain all single bonds. An unsaturated hydrocarbon contains less than the number of hydrogens. Okay, so it's the number of multiple bonds, and actually the number of bonds in addition to a single bond, and or a cyclic structure. So if I have a ring structure in a compound, that counts as being an unsaturated site or part of the hydrocarbon. We're going to take a look at something called the index of hydrogen deficiency because it will help us in using some of the analytical equipment and understanding how to identify what functional groups might be present in a hydrocarbon. So the index of hydrogen efficiency, also known as IHD, is a calculated value that tells you the number of multiple bonds or rings in a structure. There is a equation for it that you can memorize. This is the beginning of the equation. We're going to add a couple things to it in a moment. Or you can draw the structure, count the number of multiple bonds and the number of rings to come up with the index of hydrogen deficiency. So it depends. If you're good at memorizing, you want to memorize another formula, that's fine. If you want to draw the structure, as long as you can draw it that it is a legitimate structure, you can do that as well. All right, so if you're going to use the equation, it is the index of hydrogen deficiency is equal to 2 times the number of carbons in the compound, sorry about that, plus 2 minus the number of hydrogens, and then that number divided by 2. Right. So if you have a index of hydrogen deficiency of 1, that means that you have 1 double bond in the structure or 1 ring in the structure. If you have an index of hydrogen deficiency of 2, it means you either have 2 double bonds, or 1 double bond and 1 ring, or 1 triple bond. All right, so remember the index of hydrogen deficiency for a triple bond is 2. You can have a index of hydrogen efficiency greater than 2 or greater than 3. So these are just examples. If you have a index of hydrogen deficiency of 3, that means you have either 3 double bonds, or 2 double bonds and 1 ring, or 1 triple bond and 1 ring, or 1 triple bond and 1 double bond. So calculate the IHD for the following formulas, and then also draw a reasonable structure. And does this structure match the index of hydrogen deficiency? I'll give you, take a moment, pause, and make sure that you can do that. So here are the structures that I drew. Let me change pen colors here. Okay, so here, we're not back. Sorry, here is C4H8. All right, if you look at this structure, I have 1 double bond. This should have a index of hydrogen deficiency as 1. Okay, if you look at the formula, it is 2 times the number of carbons plus 2 minus the number of hydrogens all over 2. This is 8 plus 2 is 10 minus 8 gives me 2. 2 divided by 2 gives me 1. Here's my structure for C4H6. I see these 2 double bonds, so I should have an index of hydrogen deficiency of 2. Plug it into the equation, I get the same thing. Here's a structure that I drew for C6H10. Make sure that yours is something similar. One thing that I need to do when I draw these structures is make sure that each carbon has 4 bonds. All right, I didn't bother to put the H's on here because I think it just adds to the confusion when you look at the structure. This should have an index of hydrogen deficiency of 2. Looking at the structure, plugging it into the equation, I have the same thing. Okay, looking at C6H6, this is one structure that you could draw. And we have 1, 2, 3, 4, and index of hydrogen deficiency of 4. The other thing that you could have drawn for this structure is the benzene ring. That's supposed to be 2. All right, here you have 1, 2, 3 double bonds, so that's 3. Plus you have that cyclical, that ring. So this should have an index of hydrogen deficiency of 4. Looking at the math, I've got 2 times 6 carbons, plus 2 minus 6 over 2. 2 times 6 is 12, plus 2 is 14, minus 6 gives me 8. 8 divided by 2 does indeed give me 4. I did want to point out that ring structure counting as 1. So benzene has an index of hydrogen deficiency 4. Okay, so we wanted to add more complexity because we don't want to just limit what we look at to organic compounds that have carbon and hydrogen. So let's look at molecules that are going to be a little bit more complex, meaning they might have nitrogen, oxygen, or some halogen in the formula. The formula is a little more complex again because we have to add those. So the index of hydrogen deficiency is 1/2 times 2 times the number of carbons plus 2 minus 8, so that's the same as before. But now we're going to subtract the number of halogens and we're going to add the number of nitrogens. If you notice, oxygen does not enter into the formula, but as we see if you use the drawing method, you do have to account for that. So let's take a moment and look at the index of hydrogen efficiency for the following structures. You can use the formula or the drawing a reasonable structure. Oh, hang on. I'm going to draw the structure for these first. If I look at this first one, I see that there's 6 carbons. 1, 2, 3, 4, 5, 6. And it says I have 12 hydrogens and 6 oxygens. Okay, well, it makes sense to put an oxygen on each one of those carbons. And then I'm going to make these alcohols. And that uses up 6 hydrogens and 6 oxygens. So now I have 6 hydrogens left over. I'm going to put 2 of them on this structure, and I'm drawing it a little weird because I'm out of screen on that side. That's 2, so I only have 4 more, but I have 5 more carbons, so I'm going to put in a double bond. Okay, if I put in that double bond, that means I have to put a hydrogen here. 1, 2, 3, 4, that doesn't need one. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each of my carbons has 4 bonds, so that is a legitimate structure. I see that my IHD, it's a D, is equal to 1 for this structure because I have that 1 double bond. Okay, so if I were going to use the equation, it was 2 times the number of carbons plus 2 minus the number of hydrogens minus the halogens, which there aren't any, and plus n's, there aren't any, and then this will be divided by 2. 2 times 6 is 12, plus 2 is 14, minus 12 gives me 2. 2 divided by 2 gives me 1. Well, that's good. All right, so let's take a quick look at the next one. Oh, I have 5 carbons. 1, 2, 3, 4, 5. 1 nitrogen, an oxygen, and 9 hydrogens. I'm going to give you a trick that I think works well for me. Whenever I see nitrogen, I'm going to make this last thing a nitro. If I end up with leftover hydrogens, then I can convert this to an amine, but I'm going to leave it there for now. I'm going to have an oxygen, so I'm going to put an oxygen just here. I have 9 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. This should give me an IHD equal to 2. Okay. That was kind of my thinking in applying these. I got 9 hydrogens. Let's fill in the carbons. Let's see how many I have left. I only had 1, so I opted to make that a alcohol. And this is, you should end up with functional groups that you're familiar with. Okay, so let's look at the math. 2 times the number of carbons, that's 2 times 5, plus 2 minus the number of hydrogens, plus the number of nitrogens, all over 2. 2 times 5 is 10, plus 2 is 12, minus 9 is 3, plus 1 is 4. 4 divided by 2 gives me 2. Again, I would opt towards the drawing as opposed to memorizing